Dear participants, welcome to the 5th International Congress on Human-Computer Interaction Optimization and Robotic Applications. The symposium is organized by Tokat Gazi Osman Pasha University from Turkey and National Technical University, Kharkiv Polytechnic Institute from Ukraine. The symposium is also technically sponsored by IEEE Turkey section. Thank you for your scientific contribution and support the symposium. Let's start the session if you want. First paper belong to dear Ahmet Said Dedeoğlu.
I am ready. I can.
If you are ready, you can start your presentation. Sharing your screen.
Hello, my name is Ahmet Said Dedeoğlu. I am a research assistant at Gaziantep University, Electrical and Electronics Engineering Department in Turkey. Today in this presentation...
Sorry, you have 10 minutes, please.
Okay. Today in this presentation, I'm going to talk about our study, automatic segmentation of maxillary sinus. Let me first briefly introduce the content of the presentation. I will begin with the definition of the maxillary sinus, and I will briefly introduce the anatomy and functions of the sinus, and also to understand better the importance of our study, I find it useful to know the MS-related diseases and operations. And also, I will mention about the data sets that we use in our study. How did we prepare our data sets? Where did we get it? And also, I will explain our deep learning model and the training procedures. And lastly, we will look at the results of our study. We have 4 pairs of sinuses in our body, actually in the skull. They are called frontal, ethmoid, sphenoid, and maxillary sinus, and all of them called paranasal sinuses. Maxillary sinus is the biggest of the paranasal sinuses, and we concentrate on maxillary sinus in our study. Functions, the main function of the maxillary sinus is not clearly understood actually, but anyway, in the literature, it is thought to have some functions like warming and humidifying the inspired air from the nose, and also giving resonance to the voice, and also reducing the weight of the skull can be counted among the functions of the maxillary sinus. Here in the first image, we see the 3D reconstruction of the maxillary sinus, which is done in the 3D slicer program. And it is generally compared to a pyramid in the literature. It is generally called pyramidal shaped cavity, but of course, its shape differs from person to person. There are some factors, situations that affects the morphology of the sinus. For example, MS is closely connected to the posterior teeth, upper posterior teeth, and sometimes roots of the teeth could cause convolutions in the sinus floor, and it changes the shape of the sinus. And for clinicians, it is very important to know the relationship between these teeth and the maxillary sinus floor to prevent the complications during any dental procedures or any surgeries related to MS region. And at the bottom figure, if you look at there, it is also very common to have little bony projections inside the sinus, as we see in the figure. They are called septum, and they can be in many different sizes, locations, and directions inside the sinus. And it affects the shape of the sinus, of course. And these variations are very important for the segmentation performance. And MS-related diseases and operations, I think it is also important to know the disease and operations related to maxillary sinus to emphasize the importance of our study, or also MS segmentation. Sinusitis is the first and most common disease when we talk about the sinuses. It is the inflammation of nasal cavity and paranasal sinuses, as we see in the figure in the first image. Before any operations about the sinus region, like implant placement, it is very important to know if the sinus have inflammation or not, and it should be treated before the surgery. Generally, antibiotic drugs are enough for the acute sinusitis, but for the chronic one, a surgery called functional endoscopic surgery is a way to treat the disease. At the bottom figure, we see visual explanations of stage of sinus floor augmentation surgery. Generally, this operation is done for implant placement. And for these kind of operations, it is very important to have detailed understanding of the maxillary sinus morphology. There are 55 persons CT scans in our data set. The scans are taken from Gaziantep University Hospital. And we see some example images from our data set. These are some slices from different CT scans. As we see, we have various types of sinuses in the data set. I put here some examples. For example, in the figure A, we have completely clear sinuses. And in the figure B and C, we have partially opacified sinuses. And at the bottom row, we have examples of completely and almost completely opacified sinuses. 47 scans used for the training data sets and 8 scans used for the test data set. The sinuses are labeled layer by layer, one by one, using the 3D slicer program. The DICOM files of the slices exported from the program and converted to PNG format to use in the training of the model. Here, these are some examples of our last original and ground truth mask images. These are the images and masks used for the model training. These are all 512 by 512 pixels. In the literature from medicine-based works, generally manual and semi-automatic segmentation models are used. But of course, these methods heavily depends on the doctor's experience. And also slice by slice segmentation is a time-consuming procedure and not suitable for the clinical practice. In the engineering sites, deep learning-based models are the most frequently used models for the segmentation. And since the release of the UNet model in 2015, U-shaped frameworks are the most frequently used models. We see here the original UNet architecture. Our segmentation model also based on the U-shaped architecture. And as we see here, it has a falling path, left part. It is called encoder, and it has a rising path, right side. It is called decoder. In our network, instead of using normal encoder, we have used VGG16 model for the encoder part. VGG16 has, as the name implies, 16 trainable layers, 13 convolutional and 3 dense layers. We have used the parts before the dense layers as the encoder of our model, 13 convolutional and 5 max pooling layers. The network was pre-trained with the ImageNet dataset, and instead of starting with random weights, we have used the pre-trained network weights. and all the layers are trained from scratch according to our CT scan images. And in the decoder part of the network, 5 upsampling layers are used against the 5 max pooling layers in the encoder part, and also various convolutional layers. The input resolution of the image to the network was 512 by 512, and it is decreased in the encoder part until 16 by 16 pixel resolution. And in the decoder part, it is again raised up to 512 by 512, thanks to these 5 upsampling layers. Here we see our training hyperparameters. In order to determine these hyperparameters, we have trained so many models, and we have decided these parameters according to the results. And we did all our work on Google Colab platform. And if you remember from previous slides, the MS region is the minor percentage of the CT scan, and it results a data imbalance problem between foreground and background. And the mask region is generally a small portion of the image, and the dice and focal losses are the 2 very common ways to overcome this problem. And we have used an equilibrated combination of these 2 losses, which is called focal dice loss. And here we see the model's performance results on the test data set. We have compared 4 segmentation results. We have trained 2 different types of models, normal UNet model and the UNet model with pre-trained VDG16 encoder. And both of the models trained with dice loss and focal dice losses separately. And as we see from the table, the models trained with focal dice loss gave better results compared to the ones with dice loss. And the model with VDG16 encoder trained with the focal dice loss gave the best results among all the models. You can see the results in the first row.
Dear, please speed up.
Okay, the last slide.
Time is over.
Here in this page, we see the visual results of the segmentation, and we can conclude also from the visual results. The VGG16 encoder model with focal dice loss is the best model. Thank you for listening.
Thanks for your presentation. Dear participant, do you have any question about the paper? Okay, no questions. Thank you again. I wish you success.
Thank you very much.
Dear Auskultur.
Yes, Doctor.
Okay, if you are ready, you can start your presentation.
I'm ready. Yes, Doctor. Thank you. Can you see my share?
Yes, you have 10 minutes, okay?
Okay. Okay, Assalamu alaikum everybody. Assalamu alaikum, dear Prof. My name is Muhammad Kadir. I'm master student, computer engineering, Karabük University, Turkey. Today I will present student performance prediction using machine learning based on generative adversarial network. First, we have outline consists of introduction, problem statement, objective, literature review, methodology, experimental result, and conclusion. Introduction. Artificial intelligence does not aim to replace a human intelligence, but rather to create a set of processes that perform a task far from a human intelligence. Artificial intelligence research has made a significant contribution in many fields, including the field of education, to improve the lives of students and faculty members. Problem statement. The problem that we aim to address is the challenge of accurately predicting the academic performance of students. Traditionally, educators have relied on student historical academic data and other demographic factors to make a prediction about their future performance. However, this prediction may not always be accurate, and there's a risk of overlooking a student who may be at risk of poor academic performance. Furthermore, there's a need to improve the accuracy of predictive models by incorporating data from multiple sources, as well as the challenge of ensuring that the model is robust and reliable. Objectives. We worked on 3 objectives. The first one, development of generative adversarial network-based data augmentation algorithms. The second one, development of machine learning models based on generative adversarial network algorithms. And the third one, evaluation of student performance prediction based on the proposed model by using performance measures such as accuracy, recall, and F1 score. Here we have some previous studies. In this table, we mentioned reference for each study, and method include algorithm used, KNN, SVM, and naive-based decision tree, logistic regression, and so on. Also, I mentioned some simple description for each study. And also here we have the accuracy for each study. We notice that the SVM algorithm and KNN algorithm achieved the high accuracy. This is the flowchart of our method. Firstly, we work on student performance dataset. It's a label dataset, and we divided it into 3 classes according to the final score, which range from 0 to 20. The first class, poor class, from 0 to 9, and the second class, fair class, from 10 to 14, and the third class good, from 15 to 20. And after that, the second step, we analyzing the data to see the distribution and correlation between variables. And after that, we performing data pre-processing to ensure the quality of our data set and prepare it for machine learning modeling. Specifically, we check for missing value and label encoding. And after that, we're splitting the data and implementing 5 machine learning algorithms: decision tree, random forest, linear SVM, and RBF SVM, and KNN algorithm, and modeling it and getting result. This is the first model. We work on it before implementing data augmentation algorithm. The second model, we work on it after pre-processing step, we implementing data augmentation algorithm to increase the data value, and after increasing data value, we merge the new data with real data set and splitting it and implementing the same 5 machine learning algorithms and modeling it and getting results and comparing the result before and after data augmentation. This is the flowchart for GAN architecture. GAN algorithm is a type of unsupervised adversarial network designed to address generative modeling issue. It consists of 2 neural networks. The first one is generator. It consists of 4 dense layers, and it's responsible for generating new data by taking random noise as input, and the output will be the fake data. It's look like the real data. And the second neural network, it's discriminator. It's responsible for discriminate between real and fake data by taking the input from 2 sources, real data and fake data, and the decision will be if the discriminator could discriminate between real and fake data, the decision will be not, and we will use a backpropagation algorithm to adjust the weight and repeat the same operation until the discriminator couldn't discriminate between real and fake data. So the decision will be yes. There will be and then the GAL algorithm is success to generate a new data that look like the real data set. Here we have the accuracy of machine learning technique used before data augmentation. This is the 5 machine learning algorithm we used, as we mentioned before. And we note the accuracy before implementing data augmentation algorithm. Also, this is the 3 classes for each algorithm. Also, this is the precision recall and F1 score evaluation matrix for each algorithm. And we note that the RPF SVM algorithm achieved the best accuracy. This is the accuracy of machine learning technique used after data augmentation algorithm. This is the same 5 machine learning algorithm, and this is the classes for each algorithm. We notice that the accuracy was improved, and we notice that the random forest algorithm achieved the high accuracy, 99.83%. Also, we notice that the precision recall and F1 score evaluation matrix for each accuracy was improved. Conclusion: our study presents a promising approach for predicting student performance, and finding explain that the augmentation of data significantly improved the accuracy and reliability of student performance prediction by using machine learning algorithms. Specifically, the random forest classifier achieved the best accuracy of 99.8%. So this study will contribute to the field of education by providing a more comprehensive and accurate model for predicting student performance, which can support informed of decision making and improve educational outcomes. And finally, thanks for listening.
Thanks for your presentation.
Thank you, sir.
Dear participant, do you have any question about the article? Okay, no questions. Thank you again. I wish you success in your career.
Thank you, sir. Thank you so much.
Dear Ensar Özkaya.
Yes, hello everyone.
You are ready to present?
Yes, I'm ready. I'm sharing my
Okay.
screen.
You have 10 minutes, please.
Okay. Can you see my screen?
Yes.
Okay. Okay, hello everyone. I'm going to talk about our paper, a comparative study of for 6D pose estimation of textureless and symmetric objects used in automotive and manufacturing industry. We did this research at Daimia IT and Engineering. Enes Doruk, our colleague, was a colleague of ours back then, and now he is a former colleague. So the content of my presentation is I'm going to introduce a bit the topic, then our proposed method how to solve that specific problem. I'm going to talk about the project pipeline which we use to tackle this problem. And then I will go into the details of this, of the steps of the project pipeline, and at last, I'm going to show you the results of our research. So our work is about vision-based automation tasks in the automotive industry. We want to have better models that do better predictions, and especially pose estimation. We see that there is a trend in vision-based automation systems in manufacturing, and specifically in the automotive industry. So we choose a specific task, which is the 60 pose estimation, which is a pretty not so easy task to achieve when you have limited hardware and budget. There are two main approaches to do 60 pose estimation from the point of view of the sensors that are used. There are ones, the RGB-D cameras, which measure depth, and then there are RGB cameras. When we look at the RGB-D cameras, they are expensive cameras. They have a low field of view, low frame rate, and low resolution usually, and that the ones that are that have these parameters very high, that are very expensive. And on the other hand, we have RGB cameras. They have other problems. When we do 60 pose estimation with RGB images, we are fighting lighting fluctuations, occlusions, and especially textureless and symmetric objects are very hard to detect with RGB cameras. But on the other hand, these things are computationally and programmatically solvable. And because RGB cameras are very low cost and high availability, it's very attractive for manufacturing industry to use RGB cameras and to solve 60 pose estimation with RGB cameras. So this is one part of the introduction. The second part is when we look at the industry in general, we see that there is a trend in robots being used in the manufacturing industry, and especially in the automotive industry. Everything is automated, and when we look at the other side of it, we want to have smart robots. We want to have robots that are agile and adaptive and don't need so much static and hard-coded programs. So we want to have AI-driven robots. And the AI industry in general is, of course, ever high data demanding than ever, especially with the we say that the higher the complexity of the AI model is, the higher is the probability of better accuracy. But the more complex our models is, that so much more data we need. So there is kind of a something that stops us from using smart robots in the industry, but on the other hand, we want to have more robots so that we have better automation, and that's where synthetic data comes into the game. Our aim is to solve this problem with synthetic data, because we are sure of it that synthetic data can be generated at scale without loss of accuracy and without having to lose performance from the AI models, and also without having to put maybe more than 50% of the budget only for the data. So we have a model use case. We work on this use case with a few stakeholders here in Turkey and in Germany, and we propose a platform in which we have, a robot that is going to pick a few parts, and these parts that have to be estimated in pose in 6D. And what we do is we take these CAD models and put it in our data generation pipeline. This generates us labeled data sets, which we can use directly with different training models. We chose 3 60 pose estimation models: ePose, DeepIM, and CozyPose. And these models are then going to be used in the deployment of this pipeline. So the project pipeline in general is, as I said, we take the CAD models of the data, of the models that we want, of the objects that we want to estimate the pose of. And then we generate simulation scenes in which we generate the images. And besides that, we also, of course, collect real data to validate our results. And then we train our model with both synthetic data and real data. And then we have our 60 pose estimation model. The deployment pipeline is we have real images, a set of real images. We estimate the pose of it, and that's it. So our data generation pipeline is we have up to 30 different parameters: position, rotation, light, distractor objects, background randomization, color randomization. We randomize all these parameters to see which have the most effect, and also to increase the domain adaptation of the trained model. And here are a few examples of real images and synthetic images. The training procedure is, as I said, we have a data set containing both synthetic and real data. Our first set of data is 1,500 real data samples, then 10,000 synthetic data samples, and then 9,500 synthetic and 500 real, a hybrid data set. We train these models on a workstation with two NVIDIA RTX 3090s, and we use, in all models, we use the ADAM optimizer with an initial learning rate of 10⁻⁻⁴. And as I said, the models that we use is ePose, DeepIM, and CozyPose. I won't go into the details of these specific models, as we only used the official repositories of these models. The ones that are interested in the specifics and the specific details of these models, they are referred to our paper. And lastly, we have 250 real images for validation and to see if how our model is performing. So our results are as following. We have different metrics specified to measure the performance. In these metrics, we see that DeepIM, for example, is performing best in the hybrid model. CozyPose is performing best in the synthetic model, but in other metrics on the real and again in the hybrid model. And in the last, ePose is performing best on the hybrid data set. Lastly, not lastly, I have one more slide. We measured also the accuracy in percentage of the different objects, and we can see that also here different metrics are showing different results, but they are more or less similar. And lastly, we have the effects of randomization. As I said, we have different randomizations in the dataset generation procedure, and we see that the presence of distractor objects, which are rendered in the scene, they have the most effect on the dataset, on the model accuracy. For more details, I couldn't go in very much into the details because my time is up. But if you have any questions, please ask. And we have, our paper is also very detailed. And oh, I have one more slide, I'm sorry. This here is only a visualization of our different models. And that's it. Okay, thank you very much for listening. And if you have any questions, I'm happy to answer them.
Thanks for your presentation. Dear participant, do you have any question? Okay, no questions. Thank you again. I wish you success, dear Tayyip Ensar Özkaya.
Thank you.
Next study belong to dear Ensar Faris Şaban. Dear Faris Şaban. Okay. Dear Furkan Kutan.
I am here, sir.
Okay. If you are ready, you can start your presentation.
Okay, I share my screen. Can you see?
Yes.
Okay.
You have 10 minutes, please.
Okay, sure. Hello, everyone. I am Furkan Kutan, a master student electrical and electronic engineering in Gazi University. Today, I will present automated cerebral vessel segmentation using deep learning for early detection of cerebrovascular diseases. This is my presentation concept. First of all, I will explain what cerebrovascular diseases and imaging techniques for the detection of cerebrovascular diseases, and later then I explain image processing and deep learning-based approaches. Cerebrovascular diseases are a group of disorders that result from weakness, blocked, or extroverted blood flow in the cerebral arteries that supply the brain. While CVD may not present any noticeable physical symptoms until the brain is affected. In some cases, temporary reductions in blood flow may cause warning symptoms such as speech abnormalities, motor weakness, and memory problems. Although many diseases are included in the CVD group, stroke and aneurysm are the most common forms of these diseases at the clinical level. Stroke, commonly known as paralysis, occurs as a result of occlusion or bleeding of the arteries that supply the brain. And aneurysm is a swelling in the arteries caused by the weakness of the blood vessel walls, usually in the bifurcation regions of the cerebral arteries. MRI, magnetic resonance angiography, digital subtraction angiography, and computed tomography angiography are medical imaging techniques that are commonly used by radiologists to detect CVD, while CT and DCA are invasive methods that require contrast media administration. During imaging, the radiation emitted by the intravascular contrast media is received by the detectors and transformed into the image signals. Unlike DSA and CTA, time of flight of MRI is a non-invasive technique without contrast media administration. Therefore, time of flight MRI is preferred technique for detailed examination of the vascular structure. Purpose of the study: although cerebrovascular diseases are the third leading cause of the death worldwide, they are the primary cause of disability after the disease. In the United States, someone has a stroke every 40 seconds, and tragically, someone dies of stroke every 3 minutes and 14 seconds. Each year, approximately 30,000 individuals in the United States experience a rupture of brain aneurysm. The growing prevalence of medical imaging devices in healthcare has resulted in a significant increase in the workload of radiologists. Introduction of the study: comprehensive examination of the vascular structure formed by the brain vessel is crucial for various clinical applications, including early disease diagnosis and surgical planning. Therefore, cerebrovascular vessel segmentation is an important task in medical imaging. However, creating a labeled dataset for this task can be time-consuming and require an experienced radiologist. Therefore, complete and accurate extraction of the cerebrovascular structure remains a challenging task. In this work, two contributions are made to address challenging problems. Firstly, we present a data collection strategy based on a Hessian filtering and image processing methods. This strategy helps to obtain large amounts of training data and reduce the burden of manual annotation. Secondly, the performance of various architectures that are often used in the area of deep learning-based segmentation, such as UNet, ResUnit, ResUnit++, and TransUnit, was compared using this dataset on several evaluation metrics. Materials: the research was conducted on publicly available dataset provided by the University Hospital of Lausanne, designed for detecting aneurysm disease using computer-aided technologies. The dataset consists of top MRI images and total of 284 patients. In this study, all patients' data was carefully scanned to identify patients with high-quality images for the segmentation techniques to be developed. Therefore, table 1 in the study provides comprehensive details regarding to the machine model and scanning parameters employed for the image series of 40 patients, who were selectively chosen for further analysis. Image processing based generating labeled dataset. To achieve labeling dataset, our method involves 4 stages: Hessian-based filters, connect component analysis, gradient growing algorithms, and 3D slicer application process. The first stage of our method involves utilizing the Hessian-based filter, originally introduced by Sato et al. This filter plays a crucial role in vessel segmentation by detecting high-level filter responses in tubular structures, such as blood vessels. In this context, Sato filtering algorithm result of top MRI image as follows. The second stage of our method involved the application of the connected component analysis technique to eliminate inaccurately labeled non-vessel segments and small cerebral arteries from the segmentation marks obtained in the first step. Specifically, sections that contained vessels with a size of less than 300 voxel were identified in the 3-dimensional mask image and removed from the mask. The third stage of our method, Sato filtering and CCA algorithm were unable to fully segment the cerebral arteries, and there was discontinuity in various parts of the vessels when examining of 3D images. To overcome these problems, region growing algorithm was utilized. Region growing algorithm improved the segmentation performance by filling the areas higher than the minimum threshold value that were adjacent to the segmented regions in the output image. The last stage of our method, in order to focus on the major cerebral arteries, the vessels in sections such as the skull and capillaries were manually removed using the 3D slicer application. The thinning of vessels in cerebral arteries caused by reduced blood flow can have a significant impact on the performance of vessel segmentation algorithm. To address this issue, Hollow algorithm is used, which is included in the 3D slicer application and contain morphological operations. Deep learning-based major cerebral artery segmentation. Angiography-based imaging techniques suffer from image quality degradation, including issues like signal-to-noise ratio, artifacts, and non-uniform brightness changes. Traditional filtering methods are inadequate for detecting small and thin vessel structures. These methods can lead to incorrect segmentation of undesired extravascular regions. This work focuses on developing deep learning-based methods to address these challenges. With the scope of this, using the image processing techniques in the previous sections, labeled images of 40 different patterns were quickly obtained and utilized in the training process of UNet, ResUnit, ResUnit++, and TransUnit architectures, which are widely used in the medical field. Pre-processing methods. Deep learning techniques are required standardization process to achieve optimal performance in vessel segmentation. This process aims to eliminate variation in distribution caused by different MRI devices by converting slices of each pattern into the same distribution. The Neal and Udupa normalization techniques, which are commonly used in MRI images, were utilized in the study for same pixel distribution. Upon careful examination of the dataset, it was determined that a resolution of 800 by 800 pixels would sufficiently cover the relevant brain region for all patterns. To achieve this standardization resolution, these slices of all patterns were zero-padded, ensuring that they fit the desired image dimensions. Deep learning architectures. UNet architecture consists of two parallel parts called encoder and decoder. The encoder reduces the resolution of size of the feature map through pooling layers while increasing the level of extracted features via CNN. In the decoder, the feature map from the last part of the encoder is absent to increase the spatial resolution. The features which increase the resolution are then combined with the encoder features to preserve the important previous information. This iterative process continues until the input image size is obtained, resulting in a successful segmentation output. The ResUnit architecture was developed to address the challenge of segmenting routes in aerial images. ResUnit architecture is similar to UNet. It differs in that it includes shortcut connections in the encoder and decoder layers. Shortcut connections are integrated into each section of the encoder and decoder parts of the unit, which increases the flow of information between the layers and enables the training of deeper architectures more efficiently. ResUnit++, unlike UNet and ResUnit architecture, the decoder section of ResUnit++ includes squid and extension blocks to extract relation between channels. Additionally, an address spatial parameter pooling layer block was used to improve segmentation success in regions such as edges and corners and to increase the filter's field of view of the bridge part, which is the transition between the encoder and decoder. Instead of directly combining information from the encoder and decoder parts, convolutional attention mechanism blocks were used to increase the salience of important features coming from the decoder part using encoder information. Transunit architecture consists of integrating image transformers, the latest technology in image classification, into the unit segmentation architecture. Segmentation of regions with long-range dependence, such as organs in medical images, can be challenging, since the shape and size of the regions may differ from patient to patient. This variability can significantly impact the success of segmentation using CNN architectures. In this context, transunit architecture developed integrated segmentation performance by taking into account all the relations of pixels with each other in a global way by using transformers. Implementation details and experiments. In this study, approximately 6,000 top array slices from a total of 40 patterns were used to train deep learning architectures. Among these images, approximately 1,000 slice images were utilized for training progress, while the remaining approximately 12,000 slices were reserved for testing. In training stage, dice loss and binary concept labelers combined with Adam optimizers. The detailed parameter information for each architecture utilized in this is present in table 2. The loss function values and mean IOU metric values of the 4 architectures during the training progress process are illustrated below figures. In the left figure, it can be observed that the ResUnit++ architecture has an advantage in the learning process. It achieves faster convergence compared to the other architectures. In the right figure, display the mean IOU value on the validation set for each iteration, and it can be seen that ResUnit++ architecture achieves the highest score in terms of mean IOU value, indicating better generalization performance. As shown in table 3, the ResUnit++ architecture demonstrated the superior performance compared to other architectures across all metrics, with the exception of sensitivity. Unit, ResUnit, and transunit architectures exhibit satisfactory pixel accuracy. They were outperformed by ResUnit++ in terms of mean IOU, precision, and F-score metrics. These are in this section. We will see ResUnit++ prediction results from the test dataset. Sometimes 2D image inspection not enough for CVD detection. Therefore, volume rendering technique used for 3D inspection of patterns necessary. These are results. Conclusion: this study specifically focused on the segmentation of major cerebral arteries, which is a topic of significant interest to its association with various cerebrovascular diseases such as aneurysm and strokes. To achieve this, the study in several deep learning architectures such as UNIT, ResUnit++, and TrustUnit, which are commonly used in medical imaging. The analysis revealed that the ResUnit++ architecture produced the highest score, achieving remarkable mean IOU value. This finding illustrates the effectiveness of deep learning approaches in accurate segmentation of cerebral arteries. Therefore, this study could potentially contribute to the development of more effective methods for diagnosis and treatment of cerebrovascular diseases. In future studies, there will be focused on developing rapid and effective methods for geometrical examination of vessels, which will be more suitable for clinical use and aid in the detection of disease. Thank you for listening.
Thanks for your presentation. Dear participants, do you have any question? Okay, more questions. Thank you again. I wish you success, dear Furkan Kutan, in your
Thanks.
career. Dear Baida Muhammad. Dear Baida Muhammad. Are you online? Dear Güner Tatar.
Yes, I'm here.
Okay, if you are ready, you can start your presentation.
Okay, I'm ready. Thanks. Let me share my screen. Oh, sorry. So could you see my screen?
Yes, you have 10 minutes, please.
Okay. Hi, everyone, and thanks for coming and listening to me. My name is Güner Tatar, and my presentation topic is real-time hardware acceleration of low-precision quantized custom neural network model on Zinc system-on-chip FPGA. Let's look at the contents first, and then we will see the outline. I will start with the introduction section, and I will talk about motivation and background, and then I will introduce setup, training, and implementation of the model, and then I will talk about the performance analysis. Thereafter, we will see the conclusion and discussion, and I will conclude with the future studies at the end of the outline. So let's look at the introduction section first. We have a total of 4 items in the introductions, and I will briefly explain these items in the following slides. First one is the conventional approach to CNN and DNN, and then MPSOC FPGA architecture, FIN, experimental framework, and the PyTorch with the library of Brevitas. The conventional approach to CNN and DNN application involves actual floating point parameters. However, recent research has highlighted the redundancy involved in this approach. Consequently, scholarly investigation have provided evidence that accurate classification can be achieved by utilizing 1 or 2 bit quantization for the both weight and activation function, maybe. So incorporating low precision arithmetic and compact memory impression presents an excellent prospect for FPGA to elevate the speed and energy efficiency. So consequently, FPGA architectures exhibit superior peak performance compared to the floating point operation in binary operation. Furthermore, the reduced memory footprint alleviates the off-chip memory bottleneck by enabling on-chip storage of parameters, even in network encompassing billions of parameters. We introduced an enhanced version of the method presented in a study given reference from the paper with a focusing on improving inference accuracy. And we served a performance comparison of the network by setting the weights and activation of the models to low precision integer 2-bit. And we constructed our model using the PyTorch framework and they incorporated the Brevitas library to quantize activation and weights. And the Brevitas maybe is a PyTorch specific library explicitly designed for QAT, stands for the quantization await training. The fundamental goal of QAT is to minimize the impact of data loss accuracy in neural networks throughput to training process. This strategy actually ensures that the model's predictivity accuracy is less impact during inference. And this figure depicts that the QAT training sequence flow, and it showed that the quantization of the weight and activation function of parameter values to integer 2 bits before and after the process. Notably, our model retains the FP32 formats post and convolution layer and bias application. To achieve an integer 2 output for our model, we employ the quantrel activation function. This implementation underscores our commitment to balancing computational efficiency and model performance. By employing the quantrel method at the output stage, we can execute the quantization in accordance with the desired bit value. So the quantized activation function, quantrel quantization rectify linearity mean, is defined by the equation provided following slice and slice. So to deploy the quantization model onto FPGA hardware platforms, tools such as Onyx Runtime, FIN, and PyTorch quantized inference operator can be effectively utilized. Here we can see that our mathematical equation of this quantization ReLU activation function. So we will use quant_ReLU instead of using general ReLU function. Here when zx is equal to 0 and zy is equal to, and the k is equal to 1, the well-known ReLU function commonly employed in deep learning models surface as a particle case of the given definition. This highlights the versatility and the general applicability of our quantizing approach. And subsequently, we shall examine the mathematical computation of quantrel like this. Here is the quantization ReLU and the normal ReLU x001 parameter value. And here we can see that our mathematical equation as well. We can see that the S stands for here the positive floating point value, and the if Sx and x quantized value minus Szx less than the 0, we will get the 0, and otherwise we will get the this parameter as well. Therefore, to carry out the quantization operation that correspond to floating point yq is equal to these parameters, it simply necessitates the execution of the following equation. In this context, we can represent the XQ quantized matrices, while ZX and ZY denote the 0 points, and the S is a positive floating point scale. In numerous research applications, CNN models are extensively employed for feature extraction, classification, and object recognition tasks. These models process input data through diverse layer types, each comprising neurons responsible for storing input feature values and transmitting them to maybe subsequent layers. The composition of CNN architecture layers varies based on the application, encompassing convolution pooling, normalization, or fully connected and the flattened layers. And the convolutional and fully connected layers in particular often demand significant computational density and memory usage. So the architectural complexity of CNN can be broadly classified into 3 categories. The 50 layers, fewer than the 50 layers, we can call that the neural networks with thin neural networks, and more than 50 to 100 layers, we can give the medium network, and more than 100 layers, we can call that the deep neural network. And some references I try to give here to explain the fixed point, floating point, and the quantized models architectures. We develop our model by building upon the work in 9 and adding 4 hidden layers. We implement the quantization of both the weight and activation function to an integer 2 representation, subsequently incorporating batch normalization and the dropout layers subsequent to each successive layers. We train our model for 100 epochs with the batch size of 100 again, and which it significantly improved its performance during training and inference. And for classification, we used BCE with logistic loss, means binary cross entropy with logistic loss function, where the model is expected to predict a probability value between 0 and 1 for each class. This loss function combines the binary cross entropy loss and the logistic sigmoid function to improve numerical stability during training. The process actively accepts 2 distinct tensors as inputs, one embodying logic and the other representing labels, subsequently calculating the BCE loss between these 2 entities, unlike the general sigmoid function followed by the BCE loss function. It returns better numerical stability, gradients, and memory efficiency instead of using directly binary cross entropy loss. So we optimize our model using the ADAM optimization method. It's a classical optimization method. And we followed the algorithmic flowchart presented here to train our model, which is given in the previous slide. So the flowchart first step was randomly determining the model's weight and activation function. Next, we performed feed-forward propagation using the input dataset, and we initiated an evaluation to quantify the deviation between the predicted outcomes and the actual results, actual results. The training was terminated when we observed the error reduced to minimum possible value. Conversely, if the error exceeded the defined acceptable range, we actively updated the weights to maintain the training progression, the training process. In this case, where the epoch count was insufficient, we proactively increased it to ensure optimal model training, maybe. Here we can see that our resource consumption of Zinc 7020 system on chip. The success of deeper network in solving these problems depending on software optimization and hardware accelerator. The intricacy of such a model necessitates considerable memory allocation, frequently instigating the performance construction in the associated hardware. These intensive memory requirements invariably leads to power utilization concerns, particularly evident in portable devices relying on the battery-powered mobile devices such as electrical bicycle or electric cars. So these issues manifest as tangible challenges for the end user, impairing the efficient operation of these devices. To overcome these challenges, designers sometimes have developed pruning, neural network pooling, and tinying methods to reduce complex neural network computational density and memory requirements. So we can see that the resource consumption of the development board due to the model's limited depth, it exhibits the satisfactory resource utilization. Moreover, our model's integer-2 quantized footprint is lower than that of the full precision model. As previously indicated, that we conducted model training with 100 iteration epochs value. So this is our computer utilized for calculation. It's the basic and straightforward computer that everybody can access and train their neural network with if the network is quantized integer 1 or 2 bit, or any other floating point or full precision neural network cannot be actually trained on this computer as well. In this figure, we provide a detailed visual representation of the training and inference process. In the right figure, here we can see that there is a fluctuations observed in this test accuracy are attributed to quantization here. So ultimately, our model achieved actually 92% accuracy after a specific number of the iteration. It demonstrates that the weight and activation function can effectively operate without the need for full precision arithmetic. In other words, we can tell that the integer-2 quantization yields a remarkable high accuracy rate than the floating point architecture. And the table demonstrates the impressive performance matrices with an accuracy of 92%, indicating a high level of precision and its prediction. The latency of 5010 nanoseconds reflected actually a reasonable fast response time, allowing for efficient processing of incoming data. The throughput, it's about 200,600 images per second. It signifies that a significant processing capacity, enabling the system to handle a large volume of the data within a given time frame. And the real-time implementation of PIC-Z1 in platform in this figure further ensures that the system can deliver prompt and reliable results in real-world application. Overall, these performance indicators highlighted that the system's capability to provide accurate, efficient, and timely processing, making it well suited for various demanding tasks, maybe. In conclusion, our study has demonstrated that the feasibility and effectiveness of deploying a low precision quantized custom neural network model on a Zinc system on chip, we accomplished a successful reduction in the model's memory footprint and computational density without inducing a notable influence on its accuracy. This accomplishment was made possible through the quantization of the model's weights and activation function application of the Brevitas library and the execution of the model on the Zinc system on chip utilizing the FIN framework. Our study actually contributes to the growing body of research on hardware acceleration of low precision neural networks. The results underline the potential of these models to address contemporary problems in many fields, including network intrusion detection while navigating memory allocation issues and computational complexity inherent in existing hardware accelerator. Its question is here is that the trade-off between the accuracy and hardware complexity is a key factor in this research. Our model achieved an approximate accuracy rate, again, 92% on the UNSW-NB15 dataset. It's actually generated by the Australian Cybersecurity Centre. It's a satisfactory result given the significant reduction in memory requirements and memory complexity, maybe. And despite the promising result, it's essential to note that the limitation of this study or research was limited to specific dataset, and the model performance may vary with the different datasets. Moreover, the choice of quantization, the model to 2-bit was based on the context of study, and different maybe quantization level maybe yield different results. Looking at, there is an exciting scope for further research in this field. Maybe future work could explore different quantization level to identify the optimal balance between accuracy and computational density. We also recommend testing the model on different datasets and its various contexts to assess its performance and the adaptability. Lastly, we can say that the alternative methods for further optimization model, such as different training algorithms or optimization techniques, could be explored to enhance the model performance. And this research marked as a step forward in the field of hardware acceleration of low precision neural networks. And we believe that our findings will provide a valuable reference for researchers and practitioners interested in developing and implementing similar models. And last one is thanks for listening. And please, is there any questions or suggestions? Please do not hesitate to email by provided with first slide of presentation. Thank you.
Thanks for your presentation. Dear participants, do you have any question? Okay, no questions. Thank you again. I wish you success, dear Güner Tatar.
Thank you very much, sir.
Next paper has belong to Erkan Tur. Dear Erkan Tur, are
Yes,
you
I'm-
ready to present?
Yes, I'm ready.
Okay. You can start your presentation. You have 10 minutes, please.
Can you see my presentation right now?
Yes.
My name is Erkan Tur, and title of my study is Applying Deep Learning for Automated Quality Control and Defect Detection in Multi-Stage Plastic Extrusion Process. And for the table of contents, I will start with the introduction, then I will go to materials and methods with motivation, then results and discussion, conclusion, and I will show my references. And here is the introduction part. The plastics industry relies on maintaining consistent product quality in multi-stage extrusion processes, ensuring precise control over parameters such as film thickness, stretch, and defect detection is crucial. While sensors efficiently monitor product parameters, manual visual inspection for defect identification is prone to errors and delays. This study proposes the application of deep learning techniques to automate the defect detection in the multi-stage plastic extrusion process. By leveraging the power of deep learning models, real-time identification of defects can be achieved, leading to improved efficiency and accuracy in quality control. So for the key points for importance of automated defect detection is essential in the multi-stage plastic extrusion process to reduce errors and enhance productivity. Traditional manual inspection methods are time-consuming and prone to human errors, which can result in delayed defect detection. And deep learning, a subset of artificial intelligence, offers a promising approach for automating defect detection. By training deep learning models on a rich data set of process parameters, real-time identification of defects can be achieved. Deep learning models can analyze complex patterns and correlations within the data, enabling the detection of subtle defects that may be missed by manual inspection. The models can learn from large data sets and adapt to variations in production conditions. The main objective of the study is to explore the potential of deep learning in automating defect detection in the multi-stage plastic extrusion process. The study aims to develop and evaluate deep learning models capable of real-time defect identification. By implementing deep learning for defect detection, the industry can improve product quality, reduce production costs, and enhance overall efficiency. Real-time defect identification enables immediate corrective actions, minimizing waste and enhancing customer satisfaction. Automated defect detection using deep learning has the potential to revolutionize the multi-stage plastic extrusion process. By leveraging the capabilities of deep learning models, manufacturers can achieve real-time, accurate defect detection, leading to improved quality control and operational excellence. This study will delve deeper into the methodology, results, and implications of applying deep learning for defect detection in the multi-stage plastic extrusion process. The motivation behind this study is to address the limitations of the current manual defect detection approach in the multi-stage plastic extrusion process. Manual inspection is prone to errors, delays, and inconsistency, which can lead to higher defect rates and reduced product quality. Automating defect detection through deep learning eliminates the need for manual inspection, leading to faster and real-time identification of defects. This improvement in efficiency reduces the chances of defective products going unnoticed and minimize production delays, and it can enhance accuracy. Deep learning models can analyze large amounts of data and identify subtle patterns and features associated with defects. This enables accurate and reliable defect detection, surpassing the limitations of human visual inspection. So the motivation behind adopting deep learning for defect detection in the multi-stage plastic extrusion process stems from the need to improve efficiency, enhance accuracy, optimize quality control, and gain valuable insights. By leveraging the capabilities of deep learning, manufacturers can overcome the limitations of manual inspection and achieve higher levels of product quality and operational excellence. For the materials and methods part. To achieve automated defect detection in the multi-stage plastic extrusion process, a comprehensive methodology utilizing deep learning techniques have been employed. Now I will provide an overview of the methodology adopted for this study. A rich data set comprising process parameters and product parameters from the multi-stage extrusion process was collected. This data set includes time series data from various sensors and information on the quality of incoming raw materials. And for the pre-processing and data set split, the collected data was pre-processed, including normalization and division into training, validation, and testing subsets. The training set was used to train the deep learning models, while the validation set was utilized for fine-tuning. The testing set served as an unbiased evaluation of the model's performance. And for the deep learning architectures, recurring neural networks, they are also called as RNNs, and long short-term memory, LSTM networks were selected as the deep learning architectures for their ability to handle time series data and capture temporal dependencies. The deep learning models were trained on the training set and evaluated using the testing set. The mean absolute error was used as a performance metric to assess the model's ability to predict defect occurrence. The trained models were used to analyze the correlation between various factors, such as equipment performance, raw material quality, and occurrence of defects. This analysis provided insights into the root causes of defects and informed process optimization efforts. The primary data source for its study comprised production process parameters of the plastic film produced in the multi-stage extrusion process. These data were captured at all stages of the processes using a data logger located in the production lines. The captured data were labeled automatically, categorizing them as defective or non-defective based after visual inspection. Time series data was also collected from the various sensors installed in the extrusion process, including temperature sensors, pressure sensors, and others monitoring the performance of the equipment. Data on the quality of incoming raw materials was also collected. Over 227,000 unique data were collected. The data set was divided into 3 subsets: a training set, which comprised of 70%, a validation set of 15%, and a test set, which is comprising of the whole data of 15%. The training set was used to train the deep learning models, the validation set to fine-tune the models, and test set to evaluate the final model's performance. And the production set has 3 extruders with hoppers, 2 winders, and 6 die zones. Production line starts with a designated recipe, and production commences with order from the CPU setting. Here you can see the deep learning architectures we have used in the study. On the left figure, you can see the RNN, recurrent neural networks, and on the right, you can see LSTM, long short-term memory. The analysis of the time series data from the extrusion process required the use of a different deep learning architecture. Recurring neural networks and long short-term memory networks were chosen for this purpose due to their ability to process and learn from temporal sequences. For the RNN, the time series data was pre-processed to be in the suitable format for these models. This involved normalizing the data, transforming it into the appropriate shape, sequences of a specific length, and dividing it into a training set, a validation set, and a test set. The RNN and LSTM models comprise several layers, including LSTM layers, fully connected layers, and a final output layer. The model was trained to predict the occurrence of a defect based on the previous time steps using the mean squared error loss function. The model's performance was evaluated based on its accuracy in predicting the occurrence of defects in the validation set. And the RNNs were employed to process and learn from the time series data collected from the extrusion process. These networks are proficient in capturing temporal dependencies and patterns, making them suitable for defect detection tests. And the utilization of deep learning models, specifically these two RNN and LSTM networks, has proven effective in automating defect detection in the multi-stage plastic extrusion process. These models demonstrate the ability to capture temporal patterns and dependencies, leading to accurate predictions of defect occurrence. And here for the results and discussion part. For the model evaluation, the performance of the deep learning models will be evaluated using the test set, which has not been used during the training or validation stages. This ensured an unbiased assessment of the model's ability to generalize to unseen data and detect defects accurately. The evaluation involved several metrics to assess the model's performance. One key metric was the mean absolute error between the predicted occurrence of defects and actual occurrence. A lower MAA indicates a longer correlation between the model's prediction and the ground truth. Additionally, other metrics such as accuracy, precision, and recall will also be calculated. Accuracy measures the overall correctness of the model's predictions, while precision quantifies the proportion of correctly predicted defects out of all predicted defects. On the other hand, proportion of corrected predicted defects out of all actual defects. And these metrics provided a comprehensive understanding of the model's performance in defect detection. Here you can see the results as a mean absolute error and the root mean squared error. And it also shows that LSTM model has better prediction capability than the RRN in our study. And for the results and discussion part, the analysis of the contributing factors to the occurrence of defects provided valuable insights. The LSTM model identified that variations in equipment performance, particularly the temperature and pressure of the extrusion process, had a significant correlation with the occurrence of defects. Additionally, the quality of incoming raw materials was also found to be a crucial factor. These findings suggest that maintaining consistent equipment performance and ensuring high-quality raw materials could significantly reduce the occurrence of defects in the multi-stage plastic extrusion process. And for the conclusion part, the findings of this study demonstrate the potential of deep learning for automating defect detection in the multi-stage plastic extrusion process. By successfully identifying defects in real time, the proposed models can replace the manual inspection, leading to a substantial improvement in accuracy, efficiency, and cost effectiveness. Additionally, the ability of the LSTM model to identify the contributing factors to the occurrence of defects could provide valuable input for process optimization. In conclusion, this study provides compelling evidence supporting the use of deep learning in the multi-stage plastic extrusion process. These findings contribute to the growing body of literature on the application of deep learning in manufacturing and offer a practical solution for improving product quality and efficiency in the plastics industry. And for the implications and recommendations, these findings offer valuable insights for the plastics industry, recognizing the significant roles of equipment's performance and raw material quality in defect occurrence, suggest clear areas of focus for quality improvement initiatives. Manufacturers should invest in advanced control systems to regulate equipment performance parameters closely, such as temperature and pressure. These systems can leverage real-time sensor data to maintain optimal operating conditions and quickly identify and correct deviations, thereby preventing the formation of defects. And here are the references we have used in the study. And thank you for listening.
Thanks for your presentation. Dear participants, do you have any question about the study?
Thank you, sir.
Okay, no questions. Thank you again. I wish you success. Dear Sejma Çiçek.
I'm here. Can you hear me?
Yes. Are you ready to present?
Yes. I'll
Okay.
share my
If you are ready,
presentation.
you can start your presentation.
Can you see my presentation?
Yes. You have 10 minutes, please.
Okay. Good evening, everyone. My name is Şeyma Çiçek, and I'm honored to present our collaborative research paper titled Handling Imbalanced Data and Predictive Maintenance, Resampling-Based Approach. This work is the result of joint effort between myself and Professor Umut Avcı from Yaşar University in Turkey. In our study, we address the challenges of dealing with imbalanced data in the context of predictive maintenance. Without further ado, let us dive into the field of handling imbalanced data and predictive maintenance. So I will first start with introduction of imbalanced data and the major challenge of it. Then I'll show the utilized data sets that were used in imbalance in our work. Then we will mention about data level sampling techniques, undersampling and oversampling, and I will show you experimental flow of our work, and then we will compare the results between imbalanced and balanced data, and then we will move to the conclusion. So now let's start with the first slide. So in the context, so what's actually imbalanced data? So in the context of predictive maintenance, imbalanced data refers to a scenario where the occurrence of machine failures is far less frequent compared to the normal operating conditions. This imbalance in class distribution poses a challenge for machine learning algorithms, as they tend to prioritize the majority class and may struggle to effectively capture and predict the minority class of failures. So in the next slide, we will delve into the imbalanced data challenge specifically encountered in the industry. So predictive maintenance is a game changer in the industry, revolutionizing maintenance practices through advanced analytics and machine learnings. Today, we will delve into the world of predictive maintenance within the industry, aligning with the core focus of our article. And our research centered into two data sets. Firstly, we utilized the AI4I 2020 predictive maintenance dataset. This is a widely used benchmark that mimics maintenance data from the industry. This synthetic datasets provides valuable opportunities to explore predictive maintenance techniques and evaluate their effectiveness in simulated industrial settings. So it has 5 different failure and 6 different features. And PHM Data Challenge 2018, which presents a recent real-world data set collected from 16 Ion Mill edge tools that utilized in a wafer production process. This is our second part of our study. This is where we use the real data. In this data set, we have 4 different failure types and 24 different features. The real data set is extremely large. So it has around 14 million records, and the synthetic data set has 10,000 records. Now let's move to the slide where we show the distribution of imbalance of our data set. So we can see, as I said, in the total, this one have 10,000 and 339 are failures, which is correspond to 3.4% of minority classes and 96.6% of majority classes. While if we check for real world imbalance data, then we can see that this is almost 0%, because we have just 80 record failures, machine failures, where we have almost 14 million normal data. So the imbalance distribution in both data sets highlights the real world scenario in predictive maintenance, where failures occurs less frequently compared to normal operating conditions. And this poses a significant challenge for developing accurate predictive models, as the minority class of failures is significantly underrepresented in the data. So to address the class imbalance, we need to consider both data level and algorithm level solution. And today we will focus on data level solutions, specifically sampling technique use. And now I will move to the data level applied technique use. So there are 2 main types of sampling techniques. These are oversampling and undersampling. Oversampling involves creating synthetic instances of the minority classes to balance data, while undersampling reduced the number of instances from the majority class. And within these categories, we will apply the random oversampling, synthetic minority oversampling techniques, mode. And from undersampling, you apply random undersampling graphs and cluster centroids. So in our experiment, we will use a Weka toolkit, which is popular open source machine learning software to prepare and analyze the data for the classification tasks. And these are the classifiers that we are applied in our data sets. So you can see. If we move to our experiment flow, we can see that first we will prepare the data preparation. I prepared this so you can follow easily what I will show later. So firstly, we focused on data preparation. We divide the imbalanced synthetic data into 80% training data and 20% of testing data. It was crucial for us to ensure that all fault types were represented in both of the training and testing sets, allowing for a comprehensive evaluation. And next, we turn our attention to classifier selection and evaluation. Leveraging the power of the Weka toolkit, we employed 42 different classifiers. These classifiers were trained using the training data, and their performance was evaluated on the testing data. This comprehensive evaluation provides us with valuable insights into the effectiveness of each classifier. And recognizing the class imbalance challenge, we then addressed it by applying resampling techniques to create balanced data sets. By careful resampling the data, we aimed to overcome the bias towards the majority class and improve the classification. And we aimed to overcome the bias towards the majority class and then improve the classification performance. We selected the best performing classifiers on the imbalanced data and evaluated their performance on the newly balanced data sets. And then we compared this performance of these results. So if we now move to slide, we can see that show the results of our experiments with imbalanced data. So this figure provides a visual representation of the classification performance that we achieved by applying Weka classifiers on both the synthetic and real-world datasets. So in the figure, each bar represents a recall value, and the lighter ones represent the synthetic data set, and the darker ones represent the real data, where the dashed ones, they represent the best performing classifiers within each category. For instance, BiasNet here in the bias category performs the best for the synthetic data, while, for example, JRIP in the rules category demonstrates the highest performance for the real-world data set, and also for synthetic data set. And observing this figure, we can also see that the majority of recall values are below 0.5 generally, and many classifiers exhibit poor performance with recall values as low as 0.2 and an average of approximately 0.25. Due to the limited number of examples in the minority classes, and during the training phase, the classification model struggled to adequately represent and learn from these classes. If we move now to the 11th slide, we will compare the result that I just showed you for imbalanced data, and after we apply the resampling methods. The results here clearly demonstrate that effectiveness of techniques improve classification performance. Before resampling, these are the results. and with most classifiers achieving below 0.5. However, after sampling, we observe a significant improvement in recall values. The JRIP algorithm performed the best on the imbalanced dataset with the recall of 52. However, the balanced datasets generated using resampling technique exceed the performance of the imbalanced dataset by approximately 30%. And in particular, SMOTE proved to be better method, providing more accuracy representation of the minority classes than ROS. We can see that. Interestingly, the findings for the cluster technique occasionally outperform those of the SMOTE, just in, for example, this case. And for us, we see that actually these are very bad, even less than the original one. So it has limited success. So if we move to another slide, here is the real world data set results. This table provides an overview of these results, and the JRIP algorithm stands out as the best performed on the imbalanced real world data set. Sorry. However, due to computational issues, so we see that the applying RAS random tree 0.46 is given. So this here RAS is the best performing. So if the naive Bayes algorithm with the cluster technique and the random tree algorithm with the RAS technique exhibit some enhancements. However, so these are this cluster is less than all these because minority class the classes are low, so because of that. And now let's move to the conclusion part. So in conclusion, the findings of our study shed light on the challenges and potential solutions for handling imbalanced data in real-world scenario. Oversampling technique have shown to be effective in improving classification results, particularly for smaller data sets. They consistently outperform the imbalanced data, providing a balanced representation of the classes. However, it is important to consider the computational power and practically when working with large data sets, as oversampling may become impractical without significant computational resources. Resampling technique will provide effectiveness in balancing the data sets with the JRIP algorithm exhibiting superior performance by improving the performance by 35%. However, it is important to note that the random undersampling technique did not yield significant improvements. The cluster undersampling technique, while successful for the synthetic data, resulted in poor performance when applied to the real-world data set. This can be attributed to reduction of majority class examples, which negatively impacted classification results. This emphasized the needs to gather more data, particularly from minority class, to improve representation and enhance the performance of machine learning models. Randomly removing samples from the datasets provide detrimental, leading to a loss of valuable class information and poor performance. And additionally, the hybrid approach of combining undersampling and oversampling has shown promise for large datasets with minority classes. It is crucial to consider the computational power and practically of the chosen resampling techniques, particularly for large datasets. So in summary, addressing the challenges of imbalanced data requires a thoughtful and tailored approach. By employing effective resampling techniques, considering computational constraints and gathering more data when necessary, we can overcome the limitation posed by imbalanced datasets and improve the performance of machine learning models in real-world application. And that's from our work. So thank you for your attention, and I welcome if there is any question.
Thanks for your presentation. Dear participants, do you have any question about the presentation? Okay, no question. Thank you again. I wish you success.
Thank you. Thank you.
Dear Zeynep Sevim,
Yes, yes, sir.
are you ready to present?
Yeah. My presentation is. Yes, I'm ready.
Okay, you can start.
Mhm.
You have 10 minutes, please.
Can you hear?
Yes.
Okay. Welcome to my presentation. My name is Zeynep Sevim. I'm currently a master's student, the Artificial Intelligence and Intelligent System Department at Gümüşhane University in Turkey. The topic of my presentation is creation of new inverted microscope image dataset and proving auto-encoder models of higher accuracy segmentation of Hakat cell culture line. I'm going to focus on three main parts. Firstly, introduction, secondly, methods and materials, and finally, resultant discussions. Cell culture. Cell culture is defined as the growth processes of protected eukaryotic or plant cells under the controlled conditions. Cell culture but services and infrastructures for in vivo studies and contains basic techniques for hypotheses that the researchers can establish by which preliminary studies findings can be obtained. Cell culture techniques. Cell culture techniques generally offer a wide range of research, such as investigations of direct interactions on cells, direct toxicity tests, investigations of the effectiveness of various chemical and herbal agents on gut health and cancer cells. Effect of biotechnical methods included vaccine productions, commercial protein productions. Cell counting. The number of cells inhalations in content is very important for cell culture studies to be controlled and comparable. Cell counting can be done many staining methods. Cell staining special dyes are contained either in a microscope or with special cell counting devices. Cell counting under the microscope in an easy and inexpensive system that provides non-reportable results and is prone on user error. Although the error rate is cell counting with special devices is quite low, there are expensive and recurrent additional consumables. Related works. There are many related works. I don't have times. Limitations of literature studies. In the literature, many studies have been developed for cell or tissue segmentation in images inquiry from microscopic systems, and high accuracy results have been issued. However, the success in other files has not been issued for segmentation of cell culture line in images equines from inverted microscopes. There are still extensions of segmentation of cell culture line studies in inverted microscope systems. These restrictions can be summarized as follows. According to our literature research, the public data set consists of inverted microscope image is not available. It is difficult to prepare cell culture and labeling the cell culture line for segmentation by experts in the reference image to use it in the training of machine learning algorithms in challenging and time consuming. due to the lack of data sets for segmentation of cell culture line, there are few studies in the literature. Therefore, the success of automatic segmentation in inverted microscopic systems is not satisfactory. Contributions of recommended study. In order to minimize these restrictions in the literature, we create a new inverted microscope image dataset. It has been seen in the literature. Then classical UNet, SegNet, UNet with transfer learning approaches are quite successful in the studies that perform automatic segmentation. In the study, therefore, automatic encoder models are developed for segmentation of cell culture line in inverted microscope system, inspired by these studies in the literature. That concludes my first topic. Now let's move on to next topic, material methods. Inverted microscope in the image dataset. Any inverted microscope image dataset is created in order to analyze it. Autoencoder models developed in the study. This dataset consists of Hackett cell culture line. There are 80 images labeled by experts in this dataset. Brief information about the Hackett cells of follows. The Hackett cell line is the spondylosis transformed in portal caroncellous line, cell line derived from adult human skin, widely used in scientific research. Because their physical properties are quite similar to those of normal human caroncellous hazard cells, widely used model to study proliferation, differentiation of mammon epidermal cell, and the pharmacological activity after treatment of various skin diseases such as paraplegia. Autoencoder models in this study, high accurate autoencoder models are developed for segmentation of Hackett cell culture live in inverted microscope images. The developed autoencoder models take the raw form of the inverted microscope image containing Hackett cell culture line as input and give segmented embedded same size output. These models consist two main stage, encoder stage and the decoder stage. The encoder stage takes the raw form of the inverted microscope image and generates the features maps. The decoder stage, on the other hand, takes the feature maps predicted in the encoder stage as input and gives the segmented image as output. In this autoencoder models, in the study, autoencoder models UNet, MANet, and LinkNet with transfer learning are developed in order to increase the success of the classic models by providing less memory usage and shorter training time in the segmentation Hackett cell culture line. That concludes my secondly topic. Yes, now next topic, result and hardware configuration. In the study, hardware configuration informations. I don't have time. Performance evaluation procedures in this study for different performance evaluation procedures, namely accuracy, sensitivity, specificity, and Jaggard are used to demonstrate which segmentation approach produces better results. It is expected that the ideal approach produces higher HCC, sense, SP, and Jaggard values than the other approaches. Structural configurations of of autoencoder models. The dataset created for the training and testing of the autoencoder models proposed for segmentation of Hackett cell culture line randomly into 1880 by 20. The training and testing of the proposed model are permitted with 5-fold cross-validation. The learning rate is 0.01. The number of batch size and epochs are assigned to 8 and 500 respectively. The quantitative performance analysis, they take this chart, the result of the model successful quantitative performance analysis, science now study using the dataset generated to this study for segmentation of Hackett cell culture line is carried out in literature. The improved autoencoder models couldn't be compared with the studies in the literature. Quantitative result of performance evaluation processes for all autoencoder models performed in this study are presented in table lines. It is expected that measures segmented with the optimum autoencoder model give higher accuracy, sensitivity, specificity, and Jaggard values. As in table 1, it is clear that efficiency of the efficient net plus MRNet model is superior to other autoencoder models for segmentation of Hackett cell culture line in terms of performance evaluation procedures. The developed efficient net plus MRNet model produces the average values of HCC, SPA, and Jaggard, for example. And here are outputs of my models. Thank you for your time and attention.
Thanks for your presentation. Dear participants, do you have any question about the study? Okay, no questions. Thank you again. I wish you success.
Thank you very much.
Dear Rian El Yozbaki,
Yes, sir.
are you ready to present?
Yes.
Okay, you can share your screen and then start your presentation.
Please, do you see my screen?
Yes. You have 10 minutes, please.
Yes. Thanks, sir, for your time. Hello, everyone. This paper title is Detection and Analyzing Phishing Emails Using NLP Techniques, presented by Rayyan Sharafuddin Al-Yuzbeki, a master's student in computer science of University of Mosul, Iraq. The outline of this presentation: introduction, phishing email detection using NLP, method and tools, result and discussion, and conclusion. Introduction. Phishing is a risk associated with social engineering that preys on the gullibility of uninformed internet users to fool them into disclosing personal information. Attackers and phishers adopt the guise of genuine internet users. Phishers attempt to access a victim accounts without authorization in order to steal sensitive data, the victim identity, and other personal information. Therefore, it is necessary to stop hacking and the related illegal activity. Phishing emails are one form of phishing where the phisher sends the recipient an email using a false email address to trick them into reading the email. This enables the phisher to sway the user and profit from their personal data. In order to combat the issue, a number of anti-phishing solutions have gained popularity, including phishing blacklists, utilizing natural language processing, NLP, and machine learning for phishing email detection, and more. Number two, phishing email detection using NLP. The use of NLP technology rather than deep learning methods ignores the difference between anti-phishing email and other goals and partly ignore environmental information, which is preventing the discovery of phishing email from processing. The current literature analysis demonstrates the significance of the problems in understanding the hacking detection study tendency using NLP and machine learning. To thoroughly evaluate this research work, to summarize the findings of identifying hacking using NLP and machine learning, primarily performing upon diverse machine learning techniques have been studied in order to recognize fake emails. For the purpose of classifying emails as malevolent or secure emails, many characteristics have been created. Spoofing emails are one form of phishing where the phisher sends the recipient an email using false email addresses to trick them into reading the email. This enables the phisher to sway the user and pervert from their personal data. Number three, method and tools. In demonstrates the proposed models works mechanism in the figure, where the process begins by emailing a specific account with all of the email occurred in the planned dataset. After that, analysis checks to see if the emails are in Arabic or another language. And if they are, it examines the substance of the emails. After beginning read, emails are inspected and evaluated using three separate methods with an emphasis on the email's content rather than its address or sender. Based on the matched for these phrases, calculate a value as follows. The first one, examine each phrase's content separately and contrast it with a list of words that frequently used in phishing emails. Number two, obtaining the root of each word in the email's content and comparing it to each word's root in the list of words for the first technique. Number three, examine the phrases in the email text and compare them to a data of the sentences that are most frequently used in phishing emails. The result of the test are those compared to the figure, which is display the email's content and indicates whether it is a legitimate email or phishing email. The tools and application utilized were to keep track of every phishing email sent. A phishing system was developed using Kali Linux system and GoPhish tool. The Python programming language and libraries like NLTK, RE-Email, Pandas, IMAPLib, and others were used to compile and analyze the results and take the necessary action after determining that the emails were phishing emails. Number four, the results and discussion. The results of applying the three ways the three types of methods that given us the 7 cases to use this approach. The first three cases, each will be used only the one of them. The first one was for the list of words. The second one was the root of words. The third one was for the list of the sentences. And the cases of 4, 5, 6, that means we will use 2 approaches together and to get the results. And the last one, the 7th one, we will use all these 3 methods to get the perfect results. For the first one, when we use the common words for phishing emails, we get with the 99.5% for the legitimate emails and 94% for the phishing emails. The second one, when we use the root of words in the blacklist, we get the 99.5% for legitimate emails, and we get only the 2% with the correct for the phishing emails. The third one, when we use the common sentences of phishing emails, we get the 50% of legitimate emails with the correct, with the true, and we get the 10% only for the phishing email. The number 4, for the using two conditions together, that like the list of words and the root together, we get 94% for the phishing emails and with 99 for the legitimate emails. Number 5, using another two condition with the list of words and the sentences, the result was the 98.5% for the legitimate emails and 94% for the phishing email. The number 6, for the using also the another two conditions was the root only and the sentences, the results was 98.5% for the legitimate emails and 42 for the phishing emails. The last one, where we used the three ways or three methods together, we get the higher than the other results. We get the 99 accuracy or 99% for the legitimate emails and 96 for the phishing emails. As we see, we are showing in this table the all approach, what we are using with the all cases, and the last one was the higher than the other one. Conclusion of this study: due to the great development in the relaying of electronic economics transaction in the various fields of life in the world, especially in the Arab countries during the past 3 years, the electronic crimes associated with phishing have grown frequently. Due to the scarcity of research presents in Arabic language, there is a large gap in finding solution for treatment and elimination on phishing emails in the Arabic language, especially by methods that rely on NLP in analyzing the content of emails. And there is also a great scarcity in the availability of a dataset of phishing emails in the Arabic language. For the purpose of conducting research and studies, researchers must build on and explore additional research and studies utilizing the finding of this study to locate content-based phishing emails for messengers in Arabic and other languages, using the same test and conclusion approach. The best first result for utilizing the suggested techniques to recognize phishing emails when the three approaches were combined were 96% compared to 94% when utilizing one method, illustrating the effectiveness of combining more than one method to create successful result. Thanks for your attention, and please, if you have any question, you can tell me. Sir? Hello? Hello, sir?
Okay, sorry. Thank you for your presentation. Dear participant, do you have any question? Okay, no question. Thank you again. I wish you success.
Thanks, sir.
Next paper belong to dear Ivan Ralev.
Yes, I'm here.
Are ready to present?
Okay.
Okay, if you are ready, you can start your presentation. You can share your screen.
Okay. Are you see my
Yes.
presentation?
You have 10 minutes, please.
Okay. Dear professor, colleagues, and guests, my name is Ivan Ralev. I'm a PhD student at the University of Russia. Today I'm going to present our paper co-authoring with Professor Nikola Sabev. The following topic is designing a system for data processing and visualization in the public health system. The pandemic spread of COVID-19 over the past 2.5 years has had an impact on the social and working life of the population. This puts the modern world in extreme conditions and the need to take quick, decisive, and dynamically changing measures that require global containment of this infection and its spread. One of the negative consequences is the reduction of people's trust in state institutions and in particular in the health system. A major factor influencing this problem is the spread of a significant amount of fake news. A solution to the described problem is a good information policy on the part of the health authorities aimed at vulnerable groups of the population. The fourth is conducting a survey among the population regarding their attitudes towards immunization and health policy, which lead to the need to process large volume of data. For a qualitative analysis, it is also necessary to compare the new, the new information with previous surveys. Manual processing of this data would increase the patient time and the end result could be ineffective and even meaningless. The program Statistica is one of the most common and well-known statistical data processing and analysis system. This is due to the fact that in many schools and universities, students are training with its functional capabilities. Statistica can be defined as software designed for data analysis. Another commonly used method is to use an Office program to process table or text. An example of such products are MS Office and LibreOffice. The user has the option to load a file in CSV format. This slide presents the current implementation. After displaying the main window, the user must specify the path to the file. The work algorithm for visualizing the information in tabular form can be described by the following sequence. Open the file. Each line is 3 character by character and represents a separate array elements. A line number and array structure is created in which the information about each read line from the CSV file is stored. Index 0 of the array stores the data of the list containing the survey questions, and the following in these contain the answers to the questions. Visualize the information in tabular form. The algorithm for visualizing the data through charts includes the following steps. Select the column number from the table and using a loop, create a new list containing all elements in this index from the general data list. The first element of the list contains the question and the remaining elements are in answers. As chart titles, an element with index 0 is retrieved and then deleted. The remaining elements of the list are converted into a map structure where the key is the answer and the value is how many times it is repeated in the list. Data from the map structure is pasted as values to the chart and visualized it.
If the user decides to visualize the data of a given question in a pie diagram, it is necessary to double click on any cells of the column containing questions or answers they will be visualized. This can be seen from the figure at the bottom left corner of this site. This slide presents the future implementation of the system, performing qualitative analysis of the particular survey requires knowing how user opinion has changed on a given issue over a period of time. Comparing data from survey completed by a group of people at different intervals provides solutions to the problem. It is plain to add a functional possibility for simultaneous loading of several CSV files to the current system. The questions contained in the individual files will be compared for uniformity. If in one survey they follow the same order, but in another the order is reversed, this will not be a problem. In the output, they will be stored. If a particular survey contains more questions or there are differences, only those that match will be taken. For example, if we have conducted 3 polls in the last 5 years, but in the last one, some of the questions were dropped and new ones were added, we will be able to analyze how public attitudes have changed on the matching questions. An important and necessary function is the ability to be able to examine the dependencies of a certain factor on a given response. For example, to be able to present a reference in relation to the age of the interviewers, what is their opinion regarding the placement of vaccines from the mandatory immunization calendar. A person may answer the question without expressing their true opinion on answers that they would get vaccinated against COVID-19, but on a subsequent question to mark that vaccines are produced for profit. This would cause the result to be skewed and lead to the wrong measures being taken in relation to a particular situation. Further control questions must be included in the service, on the basis of which it will be possible to filter out incorrectly completed service. The program will automatically perform this analysis and display a message with the compromised ones, removing them from the final result. This automated pre-processing would save valuable time for the person involved in the data analysis. As a conclusion, it can be stated that the implement part of the system, as well as the planned future implementation, successfully meets the set goals of project implementation, investigation of immunization coverage, and public attitudes during a pandemic. Thank you for your attention.
Thanks for your presentation. Dear participants, do you have any questions about the article? Okay, no question. Thank you again. I wish you success. Dear Esra Dinçer,
Yes, I'm here.
you are ready to present your study.
Yes, I'm going
Okay.
to present now.
You can start your presentation.
Okay, I think you can see, can you?
Yes. You have 10 minutes, please.
Thank you. Hello, everybody. Our paper's topic is, and the name of our topic is Measuring and Qualification on Camera Recordings in Wire Arc Additive Manufacturing Monitoring. The outline is, first, I will start with the related work and then relevance. After the purpose, I will go into detail about materials and methods. Finally, I will finish by conclusion. First, I want to talk about the related works. Cameras have been used in welding process to observe and control the process. There are studies where the thermal and infrared cameras are used to measure the heat and the light of the welding. A few of them are as follows. First, Rodriguez used captured information to measure the solidification and to observe the arc behavior during the deposition process. Zhang et al. Proposed a method to obtain a better image of a weld scene. They wanted to solve the monitoring problems, encounters due a greater dynamic range. For the quality of weld, early fault detection can be performed by using a camera-based approach. Hartung and his friends presented an in-process image analyzer. So these are the related works which we inspired. If we come to the relevance, I want to give you some information about short information about the welding process. Welding has been automated to avoid intensive labor requirements. Robot welding has been found more stable, safer, and more successful. However, it shouldn't be expected to achieve a welding process without any problems, while the temperature of the arc may reach to 5800. Therefore, the surface of the materials, the focus at the welding point of the electrode, the angle and the speed of the robot affect the welding quality. So the quality of welding process can only be qualified at the end of the welding. If the melted volume of the last liquid welding metal could be quantified, it could be used to prevent possible errors that may occur. So it is at the end. Some problems may arise during this process. One of them is the region under the arc has light brightness caused by the heat radiance and the reflection of the arc light from the metal surface. This may enable monitoring and detecting problems during the process. This picture shows you the nozzle of the robotic arc and the heat light during the welding process. One of the problems is if the thermal light region of the weld pool exceeds a certain set limit, this may be an indication of a high use of electrodes. This may end up deformation. If it's less than a certain set limit, this may indicate a lower amount of electrode use. It may cause a problem in welding quality. So these are the two problems related with this heat. So we focused on this problem in our study. The purpose of our study basically to increase the welding quality by checking the amount of brightness during the welding process. The weld pool brightness is calculated simultaneously to get momentary welding amount in order to measure the welding quality and stability. Briefly, what we did is we processed 3 different welding videos. We calculated the size of the thermal light regions. We used 2 different algorithms. One is k-means, the other Teijin chain algorithm to calculate these regions. And then we compared the results to find the detection success of these algorithms. What we used is we used 3 different videos taken by GWC 40T MIC thermal camera. This is the camera type we used. And by using Python programming language, we developed the codes to process the frames. The algorithms are coded using the image processing functions from the OpenCV library. These are the example images we worked on. The first one, the original image from the video, 1 frame. The second one is the processed frame. After we processed, we could display the region, heat region, and separate it from the main image. which can be seen. The steps of the process are listed as seen. The frames were read by the program, which we developed by using Python, one by one, and converted into a grayscale to process. During the process, first we thresholded the images, and then contours were determined. Highlight area pixels were calculated in centimeters square, and these results represented graphically at the end. These are the steps for each frame. This is an example, an output of the K-means algorithm. K-means is a clustering algorithm, and there has to be a cluster number given at the beginning of the process. So we run this program for 2, 4, and 8 clusters. According to our experimental results, 2 clusters performed a better separation. So we have chosen 2. Our methods during welding process, the captured camera images show hot regions in white shades, and the surrounding cooling region was in gray shades. So images have been processed and the areas have been calculated automatically. The original torch width in centimeter was used to calculate 1 pixel size, and the result is used to find the area of brightness. These images to show you how we calculated the area. Tension chain algorithm and K-means algorithms were applied and compared on the images. The results were compared. So as you can see, the green lines showing the tension algorithm success. There is more success when we use this algorithm. It detected the real heat light area, which we wanted to catch. K-means algorithm in some frames were unsuccessful, and in some frames, the detection success was lower than tension algorithm. Each frames one by one calculated. So on this table, where we show some examples, numbers, calculation results belong to 9 different frames, just to give an idea about the numbers. The success rate was found 2758, which shows that Techin algorithm was more successful in calculating the heat light area properly. The K-means algorithm runs slowly, slower than Techin. The detection success of Techin was higher. All red areas on the frames were selected correctly by using Techin chain algorithm. So the results, the goal of this work was to help to increase the welding quality by checking the amount of brightness during the welding process. K-means clustering method and Techin chain approximation algorithms have been used to calculate the size of this heat region, and we found K-means algorithm required a relatively longer calculation time, and selection success of the Techin algorithm was better. As a result, Techin chain algorithm is more successful in calculating these bright regions in the weld pool. The success rate was 28.54. Using this method, the robotic arc welding machine may be able to create a more stable and clean weld by interfering instantly. The information gathered from the calculations can be used to increase or decrease the speed, change the angle of the advancement, change the use of electrodes. So these numbers can be used to manage the process better and get a better result. That's the result. Thank you for listening.
Thanks for your presentation. Dear participants, do you have any question about the paper? Okay, no question. Thank you again. I wish you success.
Thank you.
The last paper of the session belonged to their guide, Asghar.
Yes,
Ashkar.
can you hear me?
Yes.
Okay.
Are you present?
Yeah, I'm ready.
Okay.
And also I'm the person.
You can start your presentation.
Can you, yeah, okay.
Okay.
Just a second.
You have 10 minutes, please.
Okay. Can you see my screen, please?
Yes.
Okay, so hello everyone. So I know everyone is tired, so I will try to do it fast as possible. So my name is Gait Ashkar. I'm completing my master's degree at Kocaeli University. So today we will do, I will present our article and our work in the study of various embedding for keyword extraction. So actually, overall, our study, we will use some word embeddings and various models in order to get the best and to know the best embedding models in order to see how they work and how we can develop them and improve their results. So the problem is to determine the most effective embedding technique for keyword extraction from text documents. This involves comparing and evaluating the different embeddings to identify the approach that accurately captures the semantic and contextual information of keywords. So the motivation also, it's behind the assessment to improve the accuracy and efficiency of keyword extraction in NLP, the natural language processing. So let's go with a very fast, quick background. Natural language processing is a subfield of artificial intelligence and diagnostics that focuses in the interaction between computers and the human languages. So there is many applications of natural language actually in our life, but I need to focus in chatbots. Everyone know the new ChatGPT and the Copilot, for example, the Microsoft. So some application like ChatGPT and Copilot, for example, I'm using a Copilot a lot. So you can immediately give in your instruction, your computer, and like I need to build array or I need to make some modification in my code, and actually it can help you. So basically natural language processing is the basic idea to make communication with the computer using our normal language. So actually, and also the keyword extraction is the process of automatically identifying and extracting the most important and relevant keyword of key phrases from the text document. So let's say that we have a very big data or very big large data, and if we need to read it, maybe it needs really a good time. And from this technique, really we can summarize it and we can understand it very quickly. And also it's available as metadata for indexing and decking and documentation. So key phrase extraction applications, there is many applications as I mentioned, and we are focusing here in the natural language processing. So actually there is many methods for keyword extraction. So there is supervised, unsupervised, semi-supervised as machine learning algorithms. But actually here we are focusing in unsupervised, and the word embedding is also unsupervised method. So unsupervised methods, there's many unsupervised methods like embedding based, which are working on, and there is a language model based, graph based, static set based. So let's say this workflow, this is actually the common between the all unsupervised algorithms. So let's say we have a document, and this documents includes text, and we do the pre-processing part. After that, we do some generation for the candidates. After that, we applied our algorithm. So for example, we modified keyword system. We are using cosine similarity, but if we are using another system like a frequency, so you should use the frequency. After we doing our algorithm implementation, our algorithm here, we need to ranking. For example, we have the most highest rank here. So basically, this is the highest rank. This is the most important key phrases in our text. This is basically the workflow. Here we go some in details. We see we have the input, the document, we do the pre-processing, feature extraction, and we applied our algorithm. After that, we do the scoring, we take the results, and after that, finally, we do the evaluation. So our materials and method. In our method involves extraction keywords in the basis for the conceptual relationship on the phrase. So if we looking the statistical method like frequency, when the extraction keyword, they only consider frequency. For example, the statistical methods just focusing in how many the keywords recurrent or re-mentioned in the text. But in our system, we modified the keyword system, which is a keyword extraction method that uses BERT embeddings to extract keywords that are the most representative of the underlying text document. So as I mentioned, it's an unsupervised method, and here I will explain it very clearly. So we have the document, and we need to take the feature of that document. For example, in our work, we take just the abstracts of our documents, and we do the pre-processing part, like noise removal. For example, if there is some phrases, just 3 or 2 words, we deleted them. We make the pre-processing and make the cleanup for the data in order to get a good results or a better results. After that, we do generation for the candidates. When we do the candidates, we do the embedding for the candidates, also for the whole text, and we take the cosine similarity between them. And when you take the cosine similarity between them, after that we get scores, and we take the most and the highest 10 of the scores, and we take the keyword, the keywords or the key phrases of the text. So actually we use 10 different models. I know that we do not have time, so I just will mention them. We use Alpert, LMP and Glove, Elmo, Part, Reporta, DistalPert, and 10 actually I will show them later in the table. And we use 7 different datasets. All the datasets are for the computer science and articles, just the CIMA-EVAL 2017, it contains computer science and some material science and physics. So here our datasets, we have 7 datasets: InSpec, KDD, CrabVN, Nagilan, CIMA-EVAL, and CIMA-EVAL 2010, 2017, WWW. So some of them, it's already abstracts, and other, there is no abstracts. We do the, let's say, the extraction of the abstracts of the articles, and we continue the implementation. And here we actually applied the evaluation matrix of the 2. We applied the confusion matrix based and ranking based matrix. Also, we applied some statistical measurements. And here we get the results. If we see, we have 10 models in the left, and in the all experiments and all results, we get the all MPNet based version to get the highest results. So our little champion here is the all MPNet. So he get the highest result in confusion matrix, also in ranking based, as it's shown in the tables. Also in the relevant keyword, it's get the highest results. So here the Vertman test for the InSpec, actually it get, if we see in the number 2, the M2, that means the model 2, which it's, as I mentioned, our little champion. So our conclusion, so based in the confusion matrix based scores, the LMPNet based version 2 takes the highest marks and perform the best performance. After that, the DistalPert it's got some, let's say, the second highest performance. So in conclusion, it's our study actually highlights the importance of selecting the appropriate embedding model for keyword extraction, and this helps the researchers and anyone to can improve the accuracy or maybe use this model in order to do another works and researches. So thank you for listening, and any questions, I'm ready to answer that. I hope
Thank you. Thank
you
you
heard me.
for,
Oh, okay. Okay.
thank you for your presentation.
Thank you.
Dear participant, do you have any question about the presentation? Okay, no question. Thank you again. Dear Faris Shaban, are you online? Dear Bayda Muhammad, are you online? Okay. The last session of the symposium is over. Dear participants, thank you for your attending. Thanks for your contribution. I wish all participants continued success. I would like to end this session. Have a good evening. Good luck. Hope to see you at other symposium, other sessions.
Thank you. Have a good evening.
Thank you.
Thank you.
Thank you, Chef.
Thank you again. See you soon.